Okay, so let's solve this problem of telluric acid, which is known to be a diprotic acid. So let me show you the telluric acid, which is shown as, their structure looks like this. There are a lot of protons and you can lose it. The chemical structure is H2TeO4, but it's a telluride and atoms are connected by 6 OHs. But this OH, they lose the proton over there. And this weak diprotic acid, you need to know the equilibrium constant for acid. And there is a losing first proton, and this is the losing second proton. And they are going to ask you or calculate the concentration of H plus and H5TeO6 minus, which is a losing first proton, and losing second proton from the H5 compound, and what will be those concentration, and they give that 0.25 molar concentration solution of this initial compound. So this is an initial condition that we know. And then they ask what will be also the pH of this solution. So we need to know the concentration of H plus of this compound, H5 compound, H4 compound, finally pH on this. But these two are very easy relationship because pH is nothing but log of H plus compound. Okay, so as long as we know H plus, we know what it is. So the really heart of the problem is to really understand what is the meaning for the value given up here is a Ka1, so losing first proton, and losing Ka2, equilibrium constant for losing second proton. So this is your original acid. After losing H plus, H6 becomes H5, TeO6 minus. And this compound then becomes H4 TeO6 minus for the second ionization, which is losing the second proton here. And so the definition of K1, and it starts from here, it can be H6 TeO6 in the bottom and H5 TeO6 minus and an H plus. And this value is very small, and this is a very important insight that you need to develop from this compound. And for the second ionization, H4 TeO6 2 minus being generated from H5 TeO6 minus. It's just a matter of the bookkeeping, and this is a very, very small. So this is one thing that important concept that I would like to highlight in the purple color here. So you have this H6 compound, right? And then you are going to lose H plus here, and then become H5 TeO6 minus, and you're going to lose H plus here, and then there will be a H4 TeO6 2 minus. So this is a case of scenario for Ka1, Ka2, and it's going back and going back. So one important concept here is I am going to actually make this one is as a big, so to kind of to visualize the concentration magnitude is really large here, okay? Because this is that's the value for the first ionization, that's the value for second ionization, and as you can see that this value, although is small, so you start from 0.25 molar concentration, as it says, so 0.25 molar concentration of this initial compound. You start from this, and you generate something very small, and this is even smaller. right? So think about you have $1 million here, and you use let's say $100, and that's like $100 you have in your pocket, and from $100 you're generating 1 cent out of this. So this proton generated from here is almost negligible compared to the proton from first ionization. So it is an important approximation that H plus is essentially, in principle, first ionization plus second ionization, right? But this is not significant, so we can just focusing on the H plus from the first ionization, and that will be a dominant factor for the H in equilibrium. Okay, so that's the underlying assumption that your answer key provided here is not going to talk about, so I want to make a comment on that. So okay, so let's go to the establishing this the ICE relationship, which is an initial. So what is your initial concentration for Ka1? So as I said before, 0.25, and then you will be none, and you will be 0, and the people just put like a little dash line there. That's a concentration, and then you're gonna lose some of the H6 original acid, and generating their conjugate base, and the same amount of H plus there. So that is a concentration of X. You're losing some, you're making some on the other side. So and as a final, you are going to say this is an equilibrium, right? Equilibrium concentration. That's a 0.25 minus X molar. And this is an X, and that will be an X molar. Because equilibrium is a net result of initial minus change. And then we're going to use this equation established for Ka1 value. So then there will be a 0.25 minus X, and this will be an X squared. And this is a value for K1 shown up here. And this, to solve this, solve for X, value of an X, right, which is a concentration. Then X is a very crucial, because if you look at that, X is a concentration H plus, and X is a concentration of H2TeO4 minus. So it is, you have to solve it for X, and this is a quadratic equation, right? And I don't like it, right? And so there is a very useful assumption that to make your life easy. So let's think about the situation, what we call when you say weak acid. 0.25 is a large number compared to a small change shown up here, right? This is a small change. So minus X, this is going to be, we are going to say 0.25, because 0.25 is much larger number than X itself. So I can just make it 0.25. If I have $1 million in my bank and I'm spending $1, I still have a $1 million in my bank. So that's my analogy. So that's your approximation. And then this equation at the top becomes super easy, right? If you look at that, X squared now, 0.25 minus X becomes just a simple 0.25, and 2 10 to the minus 8. And so therefore you can solve it for X is square root of 0.25 times 2 10 to the minus 8, and then the X value is now 7.1 10 to the minus 5 molar. So we just solve it for X. And that X has a physical meaning, as you can see from here, as you can see from here. So it's actually the easier two answer is this. H plus concentration, which is an X, right? Which is 7.1 10 to the minus 5. and this is happen to be the same as established in this relationship in the shown on the table here. And then what about the more difficult concept is this one. What about the H2TeO4 This is a compound. Once you generate this from the original acid, and then you're going to generate this one. So this concentration of H4TeO6 can be taken from the relationship from Ka2. I mean, that's the nature of this, the equation established for Ka2. So let's look at the equation for Ka2 here, right? So this is an equation for Ka2, and I'm going to highlight it so you can see that. So this is an equation for established for the Ka2, and then what you start to notice here is okay, from the first ionization, that was a concentration what we call X, and this is a concentration for X, which is the same. So therefore, this concentration of H plus is going to be same as the one in the bottom. So we're going to cancel out. So what we want to know, what is called H4TeO6 is same as actually Ka2 value, and the answer is shown up here. So to say the same thing now, okay, so what I'm saying here is, okay, so this one is looks because of these two values shown up as the same, that's essentially the same as Ka2. And I can simply write it down, the value of 10 to the minus 11. Okay, so I answered those questions regarding the concentration. And finally, what is your pH? pH is minus log H plus. So that's 7.1, 10 to the minus 5, and that's the value is 4.2 pH. Okay. So once again, this is a weak diprotic acid, means you can lose first proton, you can lose second proton, and the weak means these values are very, very small. So the concentration of the conjugate base is very small compared to the original, and because of that, this approximation can be happen. And also this assumption of proton concentration in equilibrium is dominated by the first protonation, and that's the concept that we use to find the value for the second conjugate base here. Thank you.